Hello, everybody. Welcome back. This is part 2 of section 3.5, where we're talking about the first derivative test. First derivative test is a check to find any local extrema, that is, local maxes and mins, while you're using the derivative. So if you recall, in order for us to use the derivative function to find any local maxes and mins of our function, we need to be able to find what's called critical numbers, or that is critical values. These are x values where we go, okay, maybe there's a local max or a min there. Remember, local maximums and minimums are these tops and bottoms of the turning points on our curve. So this turning point, that would be a local max because that's a topping out. It goes up and then turns around and goes down. That corresponds to a local max. In this case, it goes down and then turns around and goes back up. So this is a local min. The x values that those types of points correspond to, those are called critical numbers. So if we can find the critical numbers first, we can locate where the maxes and mins are if we want to use the derivative. So in order to find a critical number, we have to know where they come from. Critical numbers come from one of two things. Firstly, critical numbers come from where you set the derivative equal to 0 and solve. So that's the first thing. The second thing is critical numbers come from new domain restrictions of the derivative that the original function does not have. New domain restrictions that the derivative has. So most of the time, you can find critical numbers the first way, setting the derivative equal to 0 and solving. This one, where the derivative does not exist, these new critical numbers, this doesn't happen as often, but it happens often enough. We do have to keep an eye out for it. So as I go through, I'm going to be doing two things. I'm going to say, where's the critical numbers? First thing we'll do is set my derivative equal to 0 and solve, and then I'm going to ask myself, do I have any domain restrictions of my derivative? So each time I'm going to ask myself both things. Let's go to our problems now. We had left off last time with problem 3. And problem 3, it reads as follows. It says, suppose that f of x, now f of x is an original function. Suppose that f of x is a continuous function. That is to say that it doesn't have any domain restrictions. All values of x are good to go. You can plug them in, no problems. So if f of x is continuous, and therefore I have no domain restrictions in the original function, let's go on to read the rest of it. It says, suppose that x equal 2 is a critical number. Ooh, okay, so that's a special value. That means that x equal 2 is possibly or a max or a min. Maybe. It could be neither, but we got to test it either way. But giving it the title, critical number, that means that something interesting is happening there, and I'm going to take a look at it. So if it's a critical number, it's potentially a max or a min. Could be either one, but it's potentially a max or a min. And then they go on to give me data. They say, we also know that f prime of 1 is -3, and f prime of 3 is 10. And we know that there are no other critical numbers besides x equal 2. So this is the only one. What then can we say at x equal 2? What happens there, if anything at all? In this case, since they give us a critical number, they're really wanting us to check whether it's a max or a min. Now, in this particular case, they did not tell me what my original function was. They did not say f of x equals blah, blah, blah. And they also didn't tell me the derivative either. They didn't say f prime of x equals blah, blah, blah. They gave me data. They said x equal 2 is a critical number. So I'm going to put that on a number line. If I'm doing the first derivative test, I'm going to do a number line analysis. So put your critical number on there. And then we have to interpret this data. This says f prime of 1 is -3. Now, what does that mean? That means that I plugged x equal 1 into the derivative. So they're giving me data. They say, I plugged 1 into the derivative, and I got -3. I have to make that mean something to me. So x equal 1. let's figure out where that is. X equal 1 is over here. It's right before x equal 2. So they took some x value in this region. It happened to be x equal 1 in this case, but they took a number in this region, and they said they plugged it into the derivative function, f prime, and they get -3. So if I interpret this a little bit more, this is a negative value that I'm getting out from the derivative. What does that tell me about the original function? Remember, we had talked last time that means my function is decreasing. So what they're telling me is that my function is decreasing at x equal 1. It's decreasing there, which means that it's decreasing over this entire interval between -infinity to 2. What they've done is they've done my interval testing for me. We just have to be able to make sense of it. They plugged in 1 into the derivative and got a negative number. All you've got to do is interpret what that means. That means that my function is decreasing. Similarly, if I come over here, they say f prime of 3 is 10. They plugged x equal 3 into the derivative and got 10. Well, where is x equal 3? X equal 3 is over here. It's on this side of 2. And at x equal 3, they said what? The derivative, f prime, is positive. And a positive value for the derivative means your function is increasing. So they did all of the number crunching for us here. They said, here's some data, derivatives this, the other derivatives that. You just got to interpret it. You got to know what it means. So now that we know that, it's decreasing on one side and increasing on the other, what does that tell you happens at x equal 2, if anything? But that's what we're trying to figure out. Is this critical number a max or a min? Is it neither? Well, in this particular case, we have on the left side of 2, my function is decreasing, so I like to do a little doodle. It's decreasing on the left of 2, and then it's increasing on the right of 2. So if you have your little grid here, this is x equal 2, we have my functions going down, then going up. Down on the left of 2, up on the right of 2. So it looks like my x equal 2 corresponds to a local min. This is what they mean by finding maxes and mins using the derivative. They gave me information about the derivative, but I can infer from that data that the original function, which I can't see, they didn't tell me what it was, my original function must have a minimum there at x equal 2. There must be a local minimum at x equal 2. Why? Because my function is decreasing on one side and increasing on the other. It's going down and then it's going up. It's gotta be a turning point there. It turns around. It stops doing the going down and starts doing the going up. So it has to be a local min there. That's all that we can do for this problem. There has to be a local min at x equal 2. I can't find a y value that accompanies 2. I can't find the actual point because they didn't give me the original function. So I have to be happy with just using the x value. It occurs at x equal 2. The y value, I can't find it. Not this time. So this leads us to doing number 4. Now number 4 is broken up into several parts. So let's do part A. Now if we read this, it says, find the critical values and use the first derivative test to find any local extrema. So they want me to do all of the things we did in number 2, where we found the critical numbers and put them on a number line, but we're having to do this all in one block. So we might have to do this in steps ourselves and kind of label things. First, find critical numbers. Now those are the potential maxes and mins. Find those potential maxes and mins, and then use a number line analysis to figure out if they do correspond to maxes and mins. So our first step is first find those critical numbers. find the critical numbers. And remember, critical numbers come from two places. One, where the derivative is equal to 0, and 2, where the derivative has new domain restrictions. So first of all, let's take the derivative and set it equal to 0. That's the biggest way we're going to find any critical values. If you take the derivative of that and set it equal to 0. So let's do that. The derivative is, if you take the derivative term by term, power rule there, 6x squared plus 6x minus 72. That's my derivative function. Now what I'm supposed to do with that, I'm supposed to set this equal to 0 and solve for x. Now when I have this set equal to 0, I notice that this is a quadratic. So it would be really great if I could solve this by factoring. So let's first factor out greatest value of 6 here. If I factor out a 6, this becomes x squared plus x minus 12, because 72 divided by 6 is 12. I then can factor this part. This factors into x plus 4 times x minus 3, and this is traditional factoring. Now, I showed this in my last video, but when you have something that's multiplied like this and it's set equal to 0, they end up splitting, and you have the factors can independently be set equal to 0. So from this term, if you subtract 4 to the other side, we get x is negative 4. And if you add 3 to this side, we get x is 3. So I have two critical numbers. As far as this part, this 6, you can't actually set that equal to 0 because 6 is a number. So if you just have a number that's hanging out in front of your factorization, that part doesn't get set equal to 0. That doesn't give you anything. It becomes an incorrect statement, actually. I can set these two equal to 0, though, and solve. So I have two critical numbers. These are my local max and min candidates. We don't know if they are one yet. Might not be either one, but we can test them. Do I have any other critical numbers? Now that comes to the second instance. I said that critical numbers came from setting the derivative equal to 0, and are there any new domain restrictions of f prime? It's kind of an odd question, but one we have to consider. My derivative is 6x squared plus 6x minus 2. Is there any reason why I can't plug any x value I want in there? And the answer to that is no. You can plug any x value you want. There's no reason why you can't plug in negative 1,000, 0, 100, 91, doesn't matter. All x values are fair game here. That is to say, if you can plug any x value you want in there, there are no domain restrictions. My original function has no domain restrictions, no bad x values, and my derivative doesn't have any either. So are there any new ones? No, there is not. So we would not have any additional critical numbers gotten out of this one. I only have the two, negative 4 and 3. So then I can move on to the next step, which is doing a number line analysis. And the number line analysis, you're using the derivative function for that. So create a number line. Represents the domain of your function. It goes from negative infinity to infinity. And on this number line, put only your critical numbers. You have negative 4 and 3. Make sure you put them in the order they go in. Now these are my candidates for maybe being where a local max or a min are. So maybe this is a local max or a min. Maybe that's a local max or min. We don't know, but we got to test them. So what you do is on either side of negative 4, here and here, pick a test point, and you're going to plug that test point into the derivative. So make a note of that. You plug test points into the derivative, not the original function, the derivative, because that's what the derivative does. It tells you where your function is increasing or decreasing. So let's pick a test point between minus infinity and -4. It can be anything you like, but I'm going to plug that into the derivative function f prime. So I'm going to plug it in over here, into that. Pick a test point between -4 and 3. You can pick any number you want in there as long as it's not -4 and not 3. Pick any number you want in between there. So I'm going to pick 0. Since I'm going to have to figure out what's going on with 3 as well, I need to have numbers on the left and right of 3. So I have to pick one more test value, and it's got to be over here. Pick a test value there. You might pick x equal 4, say, but it's got to be a number that's bigger than 3. So what we're going to do is we're going to plug -5, that's my first test number, 0, and 4 into the derivative and see what's going on there. Now for this, I'm going to get my calculator. It's going to save me a lot of time punching out stuff. So let me show you a calculator trick. I can get this to show up better. There we go. Perfect. We want this thing to punch out numbers for me pretty quickly. So if you go to your y equals on your calculator, y equals, you can put any function you want in there, right? And you can graph it, but in your y equals this time, what I want you to do is I want you to put in the derivative function, 6x squared plus 6x minus 72. So we get here. I'm going to hit enter. Now, if you go, instead of graphing that, we don't really care about what the derivative looks like, so it wouldn't really make sense for us to graph it anyway. But instead of graphing it, if you go to table, which is above the graph key, you can get to that by hitting the second button here, this blue second key, and then touching graph. When you go to that, you have a table that comes up. Now, you may have already known about this, but that means if you plug in 0, you get a y value, or in this case, a derivative value of -72. Plug in 1, you get a derivative value of -60, etc., etc. It would be really great if I could make it plug in specific x values I want. Since this table is already preloaded, I can kind of just scroll up and see what the values are. It says they plugged in -5 into the derivative function I provided, and they got a value of 48. I have a value of 0 they plugged in, they got a derivative value of -72. If we go down here to 4, highlight 4, they got a derivative value of 48. So these values correspond to the derivative because the derivative function is what I put in the y equals. So if you go to the table, you can kind of use the table to help you out here. But what if these weren't nice whole numbers? What if I had to punch in a decimal? Well, here's a trick that I like to use. If you go to your table set mode, which is right here, it's above the window key. You hit the second button, table set. Your table, the one we were just looking at, is set to auto-populate. They pick out specific values of x and they put it in the table automatically, and they crank out the corresponding values for y in the y column. But what if I want to make it publish exactly, or put in exactly the x value I want? Maybe it's a decimal x value. Then you can switch down here, this independent variable, switch it from auto to ask, so that when you go to your table again now, second graph, your table is now blank. That's because it's waiting for your input to plug in your x value. So if I plug in 0, you hit the 0 key and then press enter, 0, enter, it gives you the derivative value I found was -72. What if I wanted to put in a decimal? Then 0.5, the derivative value corresponding to 0.5 is -67.5. So you can make it give you the values for whatever you input if you find that to be helpful. So we'll keep that off to the side for now. If we get back to the problem at hand, I picked test points in these intervals and I found values out for the derivative. If my derivative is 48 at -5, I'm supposed to interpret that. 48 is positive, so I'll abbreviate that as POS, it's positive. But positive values for the derivative means what? It means your original function is increasing. So I'm going to write that there, increasing. For our x equals 0, they plugged that in and we got a negative value. So that means that my function is decreasing there. And then lastly, when they plugged in 4 into the derivative, they got a positive 48 value. That means my function is increasing there. So we know things about my function. It's increasing, then it switches to decreasing, then it switches to increasing. I can use that to inform myself what my function's doing at these points. We had said that -4 and 3 were critical numbers. That means that they are potential maxes and mins. That's a special title. So if -4 and 3 are possible maxes and mins, can we figure out what they are based off of what my function's doing on either side? And the answer to that is yes, we can. If it's increasing on the left of 4, it's going up. And then on the right of 4, it's going down. What does that mean has to happen? It means that your function's got to turn around. And where's it going to turn around? At a local maximum. It's got to go up and then go down. Up and then go down. So my -4 corresponds to a local max. So let's write that here. There is a local max at x equal -4. Now let's draw a conclusion about 3 then. What's going on the left and right of 3? On the left-hand side of 3, my function is going down. And on the right-hand side, my function is going up. Left side down, right side up. So if it's going down and then going up, what has to happen? It has to be bottoming out. It has to turn around. It's got to be a local min. So we would say that there is a local minimum at x equal 3. So we had said, these are my critical numbers. They are potential maxes and mins. Now we know exactly what they are. There's a max at -4 and a min at x equal 3. We're not quite done though. To put a nice cherry on top of this pie, we need to find the y values that correspond to those x values. I want to know what the point is. What is the xy point? So if I have a maximum at -4, I want to know what the point is so I can plot it. So I want to know what is the y value that corresponds to -4. And if I have a local min, so preface that, that's local max. If I have a local min, I want to find the point associated with that as well. That's the x value 3 and the y value of question mark. So if I want to find the y values corresponding to those x values, I have to plug these x values into the original function, because the original function is what gives you y values. That's its whole purpose. That's what we've always used it for historically. So in your y equals, you're going to now put in your original function here, 2x cubed plus 3x squared minus 72x plus 5. And I'm going to go to my table, second table, and I'm going to delete these previous lines because I don't want them anymore. You just hit the delete key, delete. And I'm going to plug in the x value I wanted. Plug in -4. We get a y value of 213. You plug in x equal 3, just hit 3, enter. Then you get y is -130. So now I have an actual point that I can plot for both of those values. The local maximum occurs at that point. The local minimum occurs at that point. So what we would say in words is that the local maximum occurs at x equal -4 and is 213. The local max is 213. The local minimum occurs at x equal 3 and the local minimum is -130. All right. Let's be done with that. Moving on to the next one. Part B, we're going to try to speed this up a little bit, not take so long. This is my original function. They said, find the local max and min, and we go, okay. We're going to use the first derivative test, because, that's what they told us to do. So the first thing we want to do is find critical numbers. Find critical numbers, you take the derivative and set it equal to 0. So find the derivative. Derivative of x cubed is 3x squared. And we set this equal to 0 and solve. That's one of the conditions for finding critical numbers. The good news is this is actually pretty easy to solve. If you divide both sides by 3, you get x squared is equal to 0. If you square root both sides, you get, guess what? X equals 0. So this is a critical number. This is a shiny x value. That is a potential maximum or minimum. It could be neither. It could be neither one, but it's potentially a max or min. So it's a potential interesting thing. That's a critical number. I then have to ask myself, as part of our follow-up, are there any new domain restrictions of my derivative? Because if there were any new domain restrictions, those would be critical numbers, and I'd have to write those down too. So let's go look at my original function. Does that have any domain restrictions? My original guy. It doesn't look like it. You can plug any x value you want in there, no problem. So my original function, no domain restrictions. When I take the derivative, there it is. Does it look like there's any domain restrictions on that one? And the answer to there is no, there's no domain restrictions. You can plug any x value you want in there. No problems. The things you have to look out for are like denominators. Any x values that make the denominator 0, you have to exclude, but this doesn't even have a denominator. So we're all set. The answer here is no, there are no new domain restrictions. And so we move on with life. So given that, you do a number line analysis. Once you have your critical numbers, you're going to test whether or not that critical number corresponds to a local max or min. So we draw a number line, and on this number line, you put what? You only put your critical number. So you put in this x equals 0, and that's it. Critical number only, x equals 0. So we want to know, does x equals 0 correspond to a local maximum, a local minimum, or neither one? So in order to test this, we have to test points. Pick a point on the left and right of 0. Any x value that is to the left of 0 and between negative infinity and 0. So you might pick -1, but you really can pick any number you want, as long as you don't pick 0. Let's pick a number between 0 and infinity. Might as well pick 1. And what do you do with those? You plug those into the derivative. So we want to find f prime of -1, and we want to find f prime of +1. So take those test points, plug them into the derivative, and see what you get. Now this is where I'm going to bust out my calculator and make it do it for me. I'm trying to plug -1 and 1 into the derivative function. So in my y equal to, I'm going to clear out my previous thing. I'm going to put my derivative function, since that's what I want to plug numbers into. I put in 3x squared. I'm going to go to my table, so second table. I'm going to delete my old entries because I don't want them anymore. I'm going to hit the delete key. Delete key right there. Gets rid of the previous stuff. I'm going to plug in -1. So you hit -1, enter. -1, enter. And you look at that, you get a value of 3. If you plug in +1, you get a value of 3. Now this one is probably easy to see that without punching it in your calculator, but I wanted to show you the calculator trick. So we plug in -1 and +1 into that, and we get 3 and 3. I have to interpret this. At -1, I get 3, which is a positive value, which means my function is increasing there. Positive value for the derivative means my original function is increasing. So I'm going to write that there, increasing. I get a 3 again when I plug in +1. So this thing is still positive, which means it's still telling me that my function is increasing. And this time it's increasing at +1. It's increasing over here. So if it's increasing on the left of 0, and it's still increasing on the right of 0, does that tell us anything about 0 itself? Well, if 0 was going to correspond to a local max or min, it would have to correspond to a turning point. In other words, the intervals would have to switch. It'd have to switch from either increasing to decreasing or decreasing to increasing. It has to go from one to the other. Since there's no switch, it goes from increasing to increasing, then there can't be any local max or min, neither one, because there was no switcheroo, there was no turning around from one to the other. So our conclusion here is that, well, first off, let's say that x equals 0 does not correspond to any local extrema. So are there any other ones? Are there any other possible maxes and mins? And the answer here is no, because critical numbers are it. Like when you find your critical number, that is your one, or in this case, that is your only candidate for being a max or a min. Once you find all your critical numbers, that is it. Those are the only things you have to test to find whether there's a local max or min. In this case, we got 1. If you get 1, and we tested it this time, and we found that it was neither 1, it was neither a max nor a min, then we would conclude that not only does x equal 0 not correspond to any local extrema, but because I have no other critical numbers, there is no local extrema at all. No local max, no local min, because that I have no other critical numbers, and the critical number I did have didn't correspond to anything. So since there's no other critical numbers, there's nothing else going on anywhere. That's interesting.